So an alternative to building a basement in a building to reduce settlement is that we could put the building on piles, as shown here. The purpose of the piles is these are the piles here. The purpose of the piles is to transfer the load from the structure down to, in this case, the pile tips. So that it's sort of like building your building on stilts. And what it does is, instead of the pressure bulb emanating like this, the pressure bulb actually comes from the pile tips there. And that way, what we are doing is we are transferring the load deep into the ground where we can, in this particular case, we are avoiding this silt layer. In other words, if we were to build the building without piles, then our pressure bulb would look like that, and we would be stressing both the silt layer and some of this clay layer. By putting the piles, we completely avoid the silt layer and transfer all of our load to the clay layer. And since the clay layer is deeper than the silt, it's usually stiffer, and that can reduce our settlement. But we have to calculate the numbers. So for this particular problem, we're going to find the point of interest, H, and the stress increase at the point of interest beneath the center, edge, and corner. So we're just going to compute the stress increases. Once we've computed those, then the settlement problem is exactly as we've done in the past. So if we look at, so this is, we're going to fill out this table here, and we get the P, the A, the Q, the Z, the B, the same things, only we just have a different location for the pressure bulb. Okay, so again, what we find is we draw the pressure bulb, which is 2B, so the B is 25 feet. That means that from the pile tips, we go down 50 feet. So we get the bottom of the pressure bulb is, bottom of the pressure bulb is 21 plus 50 gives us 71 feet. So that's the bottom of the pressure bulb. And the other point we're interested in is the top of the clay is 32 feet. So again, we have, we can find our point of interest depth is, I guess I'll write it out this way, is that the, we have 71 plus 32 over 2 is going to give us our the point of interest. And that works out to be 51.5 feet, and our H is 71 minus 32, which is 39 feet. So we get that point of interest depth, 51.5, H is 39, and we're given that the weight of the structure here is 2.5 million pounds, and there's no basement, so our P is 2.5 million pounds. The area is 25 squared, 625. Our Q is simply P over A, makes it very simple, 4,000. Now the Z is different because we are going to have our Z from the measured from the pile tips to our point of interest. So it's for the center and the edge, using our methodology, for the center and the edge, it's 30.5 feet, being 51.5 minus 21. Now, for the, we're going to use our little trick to get the corner. So to use our little trick to get the corner, we're going to cut that in half. So half of 30.5 is 15.25. So that's just a matter of using the trick to use our pressure bulb. The B is 25 feet, as we see there. So then we just compute Z over B, and then we go into our chart to get our pressure bulb factor. And what do we get? Well, beneath the center, we get 0.25. Beneath the edge, we get 0.2. Now, remember, we use this 0.61. We go below the center, and then we divide the result by 4. So we get 0.6 when we read the chart, and then we have to divide that value by 4. So we get 0.15. We've done the pressure bulb so many times, I don't need to show you how to get those values. You know how to do it. Let's see, I don't think I guess I have it here. Okay. So, what do we have for, remember, this is the pattern you need to know, is that we have 1.22, 1.22 is 0.61. So we go 1.22, takes me there. 1.22 takes me there to the edge. The corner, we just go 0.61 there. So we get the 0.6 for the corner, and then we take that 0.6 and we divide it by 4. So we get our pressure bulb factors, and then what do? We get our delta sigma V is simply the pressure bulb factor times the Q. Okay, so what we want to do then is to compare two possibilities to reduce settlement. One possibility is to build a basement. Another possibility is build the structure on piles. So this is an example comparing the settlement at 10 years and infinity of a building with a basement to the same building supported on piles. And in this particular case, I'm asking for the corner settlement only. The weight of the structure is 12 million pounds. Now notice that the building with a basement has both a clay and a silt layer in its pressure bulb. So we have, if we build a basement, that may work, but we have to compute the settlement caused by the clay and the silt. Whereas the purpose of the piles is to avoid this clay layer completely by making the pressure bulb down here, and it only has the silt to be the source for settlement. So let's take a look at, so for the building with a basement, we have to get a point of interest in the clay and a point of interest in the silt. We only need a point of interest in the silt for the situation with piles. Now, so we're going to note that, first the pressure bulb completely, the pressure bulb completely covers this clay layer. So here the point of interest is at the center of the clay layer, which is 30 feet. The H is what? The H is the total thickness of the clay layer because the pressure bulb completely covers it. So that is 8 feet. And then it's double drainage because I have gravel above, I have sand below, so my HDR is 4 feet, is half of H. And then here, what do we get? We get the bottom of the pressure bulb is 125, the top of the pressure bulb is 40, so we can do these calculations. So we have the point of interest depth is equal to 125 plus 40 over 2, which is 82.5 feet, and the H is 125 minus 40, which is 85. And what do we see? We have it's single drainage, so the HDR is 85. It's equal to the H. And for this case here, excuse me, oops, the point of interest depth is going to be the 154 plus 40 over 2, which is 97 feet. And the H is 154 minus 40, which is 114. And again, it's single drainage, so that HDR is equal to H. Okay, so for the building with the basement, we have all the soil properties here. Oops. And we have to consider the clay and the silt. So we're going to have to calculate how much compression there is in the clay, how much compression there is in the silt. But now the problem becomes exactly as what we've done before. But I have to create two tables. I have a table for the clay, I have a table for the silt. And so we do our usual. We have our depth of the point of interest that we've already calculated. There they are. We were asked for the settlement at 10 years and infinity. So we have 0 minus, 0 plus, 10 and infinity. 0 minus, 0 plus, 10 and infinity. And then we calculate our t's, and we get t is equal to the same way we're doing it. C sub v in the clay is 0.64, so I have C sub v t, which is 10, over HDR squared, 4 squared. I get my capital T is 0.4 here. For the silt, my C sub v is 226, so I have C sub v t, and my HDR is 85 squared, so I get a capital T of 0.312. Okay, then my UXS, we have our Q is what? Weight of the structure minus weight of the soil removed. To get our Q, we've done that many times, so I'm not going to go through it. Our ZF in the clay is 25 feet. Yeah, so how do we get that? So there's my point of interest. That distance there is 25 feet. For that point of interest, for down here, we're going that distance. So that gives us our ZF for the two situations. We got one of the ZFs is 25 feet, the other is 77.5 feet. We get our ZF over B, ZF over B. Now, we only asked for the corner, so we're going to use the trick for the corner, which means what? We got a ZF over B of 0.42. We're going to use 0.42 over 2, 0.21, and we're going to divide the value by 4. For the other one, it's 1.29. We're going to divide that by 2 to get the chart at 0.65, and then we're going to divide the actual value when we're done by 4. So, to get our UXS, we can read the chart. I guess I don't have it. I guess I'm not going to go through it. So we're going 0.21 down below the center. I read a contour of 0.91. But then I divide the 0.91 by 4, and then I multiply that by my Q value to give me the 622. That gives me the UXS there. Now, the UXS down in the silt, I use 0.65 below the center on the pressure bulb. I get a value of 0.56, and then I divide that value by 4 to account for the corner, and I multiply again by the Q that's 2733. So I get my UXS at t equals 0 plus of 622 there, 383 there, and then to get the dissipation with time, I use the pore pressure curves at the value of t, which is 0.4, and notice that in the clay it's double drainage, so we have to use double drainage in the clay. And let's see, well, so if I'm using double drainage in the clay, what does that mean? That means that when I'm using the curves, I'm going to use there down the middle. So I use the value of t of 0.4. So I go down through the middle to t of 0.4. I read up. I get 0.47, and I multiply that 0.47 by the 622, and I get 292. So 0.47 times 622 is 292. In the silt, we're at single drainage, so remember, for single drainage, what do we do? Here are my pore pressure curves. My pore pressure curves, what do? I eliminate the bottom portion, and that means the middle of my point of interest is going to be in there. So I read off there, and in this case, my capital T is 0.312, so I go to 0.312 and I read that value. And the value that I get for that is 0.41. So I take the 0.41 times the 383, I get 157. And again, once this is done with the UXS, that's pretty much the whole problem. The U water table, you can all get that for the point of interest. I add those values to get my U. Sigma V, I look at the t equals 0 minus sigma V, and I get that. The t equals 0 minus sigma V gives me that. You can all look at those. If the t equals 0 minus figure, I guess I didn't, this t equals 0 minus figure is what is, I guess I didn't really show the t equals 0 minus figure. T equals 0 minus figure means that there's no building at all here. So I get my sigma v prime. I put that sigma v prime there. I add the 2109 to the 2307. I get 4416. That 4416 is the same for all of those. And then I just, to get my sigma v primes, I simply take my sigma v minus u, gives me my sigma v primes. So I get all my sigma v primes. I do the same thing here. I take that minus that, gives me that. These two are the same, the 4526. Then I add the 40, oops. I add the 4526 plus the 5344 gives me 9870, and 9870, 9870, and then once I have those 9870s, oops, once I have those 9870s minus those gives me those. So the same thing that we've been doing. I take those stresses, and these are the stresses in the clay. These are the stresses in the silt, and I create my clay settlement stress strain curve. I create my silt settlement stress strain curve, and I calculate the settlements the way we always have done. So, oh yeah, well, okay, and then just to remember the sigma prime p, oops, the sigma prime p's are obtained from the OCRs 1.5 to 1.11. Oops. So, 3206 for this one, 5024 for that one. And like I say, I'm not going to go through this because we've gone through it many, many times. You all know how to get the settlement by looking at these charts. But at the end, so I get the compression of the clay is, well, let's look at, so that's the compression of the clay is are those two values at the different times, 10 years, what? And there's something wrong, this should read 10 years there. So, I did that right? Yeah, 10 years, there's a mistake there. This should read 10 years. And so we have let's do the 10-year one then. So the delta H in the clay is 0.081. The delta H in the silt is 0.144. And we end up with, we have to add those two values together to get the actual settlement of the building, which is 0.225. Because we're adding the compression of the clay layer and the silt layer together, because both of them cause settlement of the building. For an infinity in the clay, it's 0.144. In the silt, it's 0.24. We have to add both of those together, and we get 0.384. Okay, I'll do the building on piles in the next video to avoid making this one too long.